Welcome to the Big Picture podcast. In this episode, we're going to be looking at how molecules interact.
I mean how they stick together?
Yeah, how do they mix and stick together?
Okay, first we have the idea of what a molecule is, right?
A bunch of atoms stuck together?
Right, stuck strongly together. So strongly together that with a molecule, you can look at it as a fundamental unit of matter. So like the most fundamental unit of water is the
water molecule.
So the fundamental unit of water is the water molecule. Now, you look at the water molecule and we all understand that it's made of atoms that are grouped together. You got two hydrogen atoms linked up to a central oxygen atom, and there's this angle between them all. Yeah, so we can distinguish what's going on within a molecule versus what goes on between molecules. Within the molecule, you've got the chemical
bonds.
Bond, yeah, in this case, a covalent bond. And those covalent bonds are strong, right? And so they hold those atoms together very tightly, so tightly that the molecule itself behaves as a fundamental unit.
Sounds good.
All right.
So what are we going to do with that?
Well, we just want to see where we are. What is it that holds the atoms together within a molecule? Right? And that would be the covalent
covalent bonds.
Bond, right? Now,
we also talked about some other bonds too, right?
Yeah, there are ionic bonds and the metallic bond. But note, we're going to be specific here toward the covalent bond.
Okay, good to know.
All right. So we know what's going on within the water molecule, but what about between molecules?
So we were talking about sticking. So how do they stick together?
Yeah, so water molecules, as we discussed before, they're really sticky. One side of the molecule is slightly negative and one side of the molecule is slightly positive. And we talked about that. It has everything to do with the geometry of the molecule and how oxygen pulls electrons toward itself, preferentially away from the hydrogens. So the oxygen side of the water molecule is slightly negative, making the hydrogen side of the molecule slightly positive. Right. We did talk about this earlier, that when you have two water molecules and put them together, you're going to have the negative side of one molecule align to the positive side of a neighboring molecule. And positives and negatives attract. And so there is an attraction, an electrical attraction between two separate molecules. And it's
okay, so what do you call that attraction?
That's a good question.
We call it sticky?
Let's call it stickiness.
Okay.
But we do need to distinguish it from what's going on within the water molecule. We're talking between water molecules. And I like to put it this way. If the force of attraction between atoms within a molecule is 100, the attraction between separate water molecules is about 5. It's much weaker.
That's a big difference.
Yeah, it's a big difference, and it has consequence in terms of the macroscopic properties of the material.
Like what?
Water's a liquid at room temperature.
And then when you heat it?
It'll turn into a gas. You're using that heat to separate water molecules from each other, and it goes from a liquid phase where all the molecules are tumbling over one another to a gaseous phase where the water molecules are moving fast, spaced far apart from each other. And if they do come in contact, it's just a collision, a bounced collision like billiard balls.
But they still stay as water molecules.
They're still water molecules. So that's a physical change as you go from a liquid phase to a gaseous phase because you still have water molecules before and after.
And then when you freeze the water?
When you freeze the water, you're pulling away energy so that those water molecules no longer have sufficient energy to tumble over one another. And the stickiness of the water molecules holds sway. All of those water molecules remain stuck in a fixed position. We call that a crystal.
Okay.
So what we're going to focus on here are the interactions between molecules. And we have just described one of them already.
Which did you describe?
The dipole-dipole attraction.
Oh, okay. So the dipole-dipole, that's where you have the positive side of a molecule sticking or attracted to the negative side of an adjacent molecule.
Yeah, exactly. Now, we talked about earlier that when you have one side of the molecule slightly negative and the other side slightly positive, we have a term for that. We call it a dipole. We say that the water molecule has a dipole, one side slightly negative, one side slightly positive. And so here's one water molecule with a dipole, and here's another water molecule with a dipole. What do you suppose we should call the interaction between those two dipoles?
How about dipole-dipole?
Yeah. Get real creative. It's the dipole-dipole attraction. If you understand a dipole, you'll understand the dipole-dipole attraction. It's merely the attraction between two dipoles.
On two different molecules.
Or between two parts within a very large molecule. Let's see, another one we can talk about is the ion-dipole. Guess what that's all about?
Let me guess. It's where an ion, which is going to have a positive charge.
Or negative charge.
Or a negative charge, but it has a charge.
Okay.
It'll be attracted to the opposite charge on a molecule that has a dipole.
Okay, let's look at the interaction between salt and water. Salt, is sodium chloride with what kind of bonding going on in there?
Ionic.
Ionic, yeah. You have a sodium ion and a chloride ion. The sodium ion's positive, chloride ion's negative. All right, so take some sodium chloride and throw it into a cup of water. What do you suppose happens?
Well, I would say that the sodium of the sodium chloride is going to be attracted to the oxygen part of the dipole.
Ah, excellent. So you're recalling that the oxygen side of the water molecule is slightly negative?
Slightly negative. So then...
Yeah. And the sodium ion is...
Slightly positive.
No, it's not slightly positive.
Very positive.
It's very positive.
Okay.
It's
absolutely
ion.
positive.
Yeah.
It's an ion.
It's all charges. It's a matter of how much charge, eh? So for an ion, the charge is as much as it can be. For a dipole, the charge is... typically when we're talking about this in context, is significantly less. Now, if you want to get into the nitty-gritty detail, I tell you, if you have sodium and chloride ions next to each other, one side's positive, one side's negative, that is a huge dipole. You have a water molecule, one side slightly negative, one side slightly positive. That's a weak dipole. But they're really the same thing, where one side's negative and one side's positive. It's a matter of magnitude.
All right, so then the sodium chloride doesn't actually separate in the water. Because that ionic bond is actually very, 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 very strong.
That's true. That ionic bond is very, very, very strong, but it is uniquely different from the covalent bond now, isn't it?
Right.
In a covalent bond, electrons are being shared.
Right. These are just a strong, strong, strong attraction.
The chlorine atom has yanked an electron fully away from the sodium, and so that chlorine is totally negative in charge, and that sodium is totally positive in charge. And here's what can happen. When you throw that sodium chloride into the water, those water molecules, emphasis on the plural, there are many of them, will start surrounding the sodium and chloride ions. The negative side of the water molecules will start surrounding the sodium ion in 3 dimensions. Likewise, the hydrogen side of the water molecules will start surrounding the negatively charged chloride ion. Now, the chloride ion suddenly finds itself being attracted to all these water molecules around it. The sodium ion suddenly finds itself being attracted to all these water molecules around it. And what happens is, like a bunch of little ants acting against something that's otherwise really strong, the sodium and chloride ions drift apart from each other to be replaced by a sphere of water molecules, each of them.
So then sodium and chloride do split.
They do.
But then it's not salt anymore.
Guess what you have before they split?
Salt.
You have sodium ions and you have chloride ions, do you not?
Yes.
Yeah. Guess what you have after they split?
Sodium ions and chloride ions.
Yeah. So get this. The breaking of an ionic bond is a physical change.
But
Whoa.
I thought you had said Sodium has very different properties than sodium chloride.
Yes. Sodium atoms are different from sodium ions, for sure. A sodium atom has 11 protons, 11 electrons. Okay?
Yeah.
It's neutral. It has no net charge whatsoever. You remove an electron from that sodium, so it has 11 protons and 10 electrons. You now have a sodium ion. Sodium ion is not a sodium atom. They sound alike, but they are completely different substances. Going from a sodium atom to a sodium ion, yes, that is a chemical change. But I'm telling you here, going from a sodium ion to a sodium ion, no, that's no chemical change at all.
Okay, I see.
So when you have salt and you throw it into the water, notice you still have the salt. It just is that those sodium and chloride ions are now no longer within a crystalline structure. Those sodium and chloride ions are now distributed throughout the water. We say that the sodium chloride has dissolved in the water, but notice you still have sodium and chloride. If you were to evaporate the water, you'd see the salt crystals start to reform.
And as the water evaporated, the sodium and the chloride would find each other again, and then they would form another ionic bond.
Exactly. Excellent.
Hence the crystals. Okay.
Yep. So we've covered dipole-dipole attractions. A good example is the attraction between two water molecules, each water molecule having a dipole, right? Then the second example we looked at was what we call the ion-dipole attraction. It's the attraction between an ion and a dipole. An example would be a sodium ion and a water molecule. The sodium ion would be attracted to the oxygen side of a water molecule because the oxygen side of the water molecule is slightly negative. And the sodium ion, it's pretty darn positive. Opposites attract. How's that?
Okay, I'm with you.
There are actually 4 we're going to talk about.
Okay.
That was
What's
2.
Next?
The third one to talk about is called the dipole-induced dipole attraction. Go ahead, turn the page. Dipole-induced dipole attraction.
Okay.
Yeah. You know what a dipole is?
A dipole is when part of the molecule is slightly positive and part of the molecule is slightly negative.
Bingo. Great. Now, let's talk about an induced dipole. For water, that dipole is a permanent situation because that's just the nature of hydrogen and oxygen atoms. Let's look at an otherwise non-polar molecule. Pick one, anyone.
Oxygen
molecule, O2, right?
Mm-hmm.
Okay. There's no polarity to an oxygen molecule, which is why it's a gas at room temperature. It's just 2 oxygen atoms stuck together by a double covalent bond. It's non-polar. You don't have electrons congregating to one side.
So the electrons are distributed equally all over those 2 oxygen molecules, evenly.
Evenly around the whole molecule. That's right. One side's not slightly positive, one side's not slightly negative. It's non-polar.
Okay.
Right? But bear in mind, the electrons are these tiny little entities that are whizzing around at really high speeds. What do you suppose might happen if a water molecule came along, say, with the oxygen side facing that oxygen molecule? Remember, the oxygen side is negative, slightly negative. How would the electrons in the oxygen molecule feel about that?
They would want to get away because the electrons are negative.
Because like signs repel. So here you have an oxygen molecule minding its own business, totally nonpolar. Then along comes a water molecule with the oxygen side facing it. It's going to disturb the situation. The negative side of that water molecule is going to literally push those electrons within the oxygen molecule away, such that one side of the oxygen molecule has a buildup of negative charge. Why? Because the electrons are running away from that water molecule. And while that's happened, while one side of that oxygen molecule has become slightly negative, the other side has become slightly positive. The electrons are now no longer distributed evenly. We have induced a dipole in the oxygen molecule. It's a dipole. It's not there normally, but we induced it.
Through the presence of another molecule that has a dipole.
Yeah. So you know what? You're going to have an attraction now between the permanent dipole of water and that temporary dipole of the oxygen. And guess what we call that attraction?
Dipole-induced dipole attraction.
Sometimes I like to call it a temporary dipole attraction, but the standard, they use the word induced, an induced dipole. Got that?
Yeah, that sounds pretty easy.
Yeah, but a little bit more complicated than dipole-dipole.
Right, because it's a situational thing.
It's just a story behind it. Okay, if you understand that, if you really do, you'll be able to answer this scenario. You ready?
Let's try it.
Once upon a time, you had this oxygen molecule minding its own business. The electrons were distributed evenly around that oxygen molecule, O2, and it was thus nonpolar. Then along came a water molecule from the hydrogen side. The hydrogen side of that water molecule is slightly positive, and the water molecule approached with the hydrogen side facing that oxygen molecule minding its own business. What happens next?
Okay, listeners, what do you think? Let's think about this.
All right, let's do the next one. We want to move along here. All right. The fourth one is called the induced dipole attraction. The story gets even a little bit more complicated. I like to use the analogy of people on a boat.
Okay, we're going on a boat ride.
So like it's a whale watching tour.
Oh, yeah.
Everybody's on the boat, and they're distributed evenly. And so the boat is even keel, right?
Okay, everybody's spread out looking for the whales.
Yeah, suddenly there's a whale on one side. What happens?
Everybody's going to run over to the port.
They run over to the port side. And is the boat even keel now?
Not if there's a lot of people and it's a small boat.
Well, electrons are like people in that boat. They're moving about randomly, right? But even without a whale coming around, what can happen is, by random chance, without the whale, you'll find the electrons congregated to one side.
Really?
Yeah, just for a moment, but then it's gone. And then a moment later, they're congregated to the other side. It's a probability thing. If you have a bunch of electrons like that, they're moving about randomly. That means there are going to be moments in which they're congregated to one side, but then another moment they're congregated to the opposite side. And if you look at it on average over time, they're distributed evenly, yeah. But for any one particular moment, take a quick snapshot, you might find the electrons congregated to one side, and the boat's not going to be even keeled. And as they're congregated to that one side, where they are, because they're electrons, is going to be slightly negative. And where they're not, it's going to be slightly positive. Here you have what's called a spontaneous dipole, or sometimes it's called a temporary dipole.
Okay.
Now, pick an atom, any atom.
Aluminum.
Iodine? Okay, good.
Iodine.
Okay, iodine is a nonpolar atom. Actually, put them together with another iodine, and you have diatomic iodine, it's I2. It's a nonpolar molecule, right? And within an iodine molecule, you'll find the electrons are distributed evenly. But what can happen is the electrons might congregate to one side just for a moment. How might a neighboring iodine molecule feel about that?
Well, those electrons are going to get pushed around as well.
Yeah. So a spontaneous, momentary, temporary dipole in one iodine molecule, it's going to have an effect on any neighboring iodine molecules, right? And that will induce a dipole in that neighboring iodine molecule. So we have what you might call a spontaneous dipole-induced dipole attraction. But when it comes to it, it's hard to tell who affected whom. Was it the first molecule that affected the second, or is the second who did the first? And you know what? The history doesn't matter. And that's why we just simply call it an induced dipole-induced dipole attraction. It's a force of attraction that occurs between otherwise nonpolar molecules.
Sounds sort of theoretical.
But it's exactly why iodine, a nonpolar material, is a solid at room temperature. It's a solid.
Oh.
Iodine molecules are sticky. Get this, they're even stickier than water.
Really?
Water's a liquid at room temperature. Iodine is a solid, but it's nonpolar. Yeah, it's nonpolar, but those induced dipole interactions, they can add up. You know how Velcro, one little hook of Velcro isn't very strong?
Yeah.
But if you have 1 million hooks?
It'd be hard to get it apart.
Yeah. So induced dipoles can add up. And this brings up another aspect of induced dipole interactions.
What's that?
The size of the molecule makes a difference. Iodine turns out to be a fairly large atom, is to say it's like a boat with a large deck. It means the probability of electrons being to one side is a little bit better than if you have a really small atom, such as fluorine. Within fluorine, the atom is so small that to congregate electrons to one side, it's just not practical. Because remember, electrons repel electrons. And if they're in really close proximity, which they are in a really small atom, they ain't going to do that.
Well, they also move really, really, really fast.
Well, they move fast in both the small and the large atoms.
But if a smaller atom, they have less area to move in.
Yes, they have less area to move in, and so that to get them congregated to one side is much more difficult. And a good way to think of it is like this. Draw a small circle. Go ahead.
Okay.
Okay, that's good. All right. I see you have it's about 1/2 inch in diameter.
Mm-hmm.
Okay, great. Now draw another circle. Make it large. Okay, like that's like 3 inches in diameter. Right? So we have drawn 2 circles, have we not?
Mm-hmm.
Now I want you to put electrons in there, a dot, just specks with your pencil. Put 20 dots in the small circle and 20 dots in the large circle. Go ahead. Okay. Notice that in the small circle, all those dots are really bunched together.
Mm-hmm.
Notice in the large circle, those dots have more space between them.
Mm-hmm.
Look at the average distance between the dots. It's greater.
In the larger circle.
In the larger circle. Iodine is a larger atom, which means when they do congregate to one side, they're still not that close to each other. That's what makes it possible for a larger atom. A small atom like fluorine, induced dipoles ain't nothing. And that is why, wait for it, fluorine is used in Teflon, the non-stick surface. Get it? With Teflon, you have a nonpolar molecule, so there's no dipoles. But because you're using fluorine atoms within that polymer, you don't even get induced dipoles. That's how it is that Teflon is a non-stick surface.
Cool.
QED. That's it.
That's very cool.
We have 4 interactions, the ion-dipole, the dipole-dipole,
Induced dipole.
the dipole-induced dipole.
Dipole-induced dipole.
Yeah, and the last one?
Induced dipole-induced dipole.
Great. Excellent. 1, 2, 3, 4. Any questions?
Okay, what's next?
What's next are a bunch of terms. Oh my goodness, look at all these terms. Let's just do a quick review of these terms.
Okay.
Right? Let me ask you.
I haven't read this chapter yet.
You did. It was a while ago. Right? you remember it all.
All right.
Solvent.
Like when you put the water as the solvent when you add salt to it.
Okay, so you have some salt and you add some water to it. You would recognize the water as the solvent.
Yes.
Why?
Because it's what the salt dissolves and separates into.
Okay, that's pretty good. We can add to that the solvent you typically have more of.
I was just picturing when when you're trying to get some goop off and you just take a little bit of
WD-40?
ethanol or
Rubbing alcohol?
Rubbing alcohol, or what do we use on the floor?
Water?
No, that horrible.
Simple Green?
No, methanol? No.
Ethanol?
No, it was in the cans when we did the tile, when we took off that.
Ooh, acetone.
Okay, acetone. That was the solvent.
The solute is that which dissolves in the solvent, and quantitatively you typically have less. Yeah, it's a question of which is more. Typically, the solvent is more than the solute. And when they come together and dissolve, they form a single homogeneous mixture called a solution. And that process is called dissolving. Excellent.
Yeah, but the big thing that you just said was homogeneous mixture.
That means if you were to take a microscope and look at it at any different part, you would see it's the same thing.
Right.
You got to stir it up. Saturated solution, what's that?
That means you can't dissolve any more solute into that solution.
So there's a limit to the amount of solute that can dissolve in a solvent?
Yeah, there's a limit, but it's based on a couple things.
Have you ever made sugar syrup?
Oh, yeah. Not as much as you, though.
You add some sugar to a pan, and then you add water to it, and you have a lot of sugar, and you're adding a little bit of water. A lot of sugar, but a little bit of water? Which is the solvent?
The sugar.
Turns out it's the water. How can that be? Remember, we said it's that which you have most of.
Oh, yeah, that's what I meant.
Okay, so here you need to think in terms of how many molecules when we talk about amount, not mass, but number of molecules. Water molecules we find are way smaller than sugar molecules. A sugar molecule is this big thing. It's a big old molecule with tens and tens of atoms all stuck together. A water molecule is really tiny. So if you had the same volume of each, you'd have like 100 times more water molecules, right? And all those little water molecules surround the sugar molecules, separating the sugar molecules from each other. Sound familiar?
Mm-hmm.
That was with the ion-dipole thing, dissolving salt in water.
Mm-hmm.
Dissolving sugar in water is very similar. The water molecules, being so tiny, get in between the big sugar molecules, and they separate them from themselves. So where before you have a large crystal of sugar molecules all piled on top of each other in a nice order, after the sugar molecules are distributed evenly throughout the water. We call that process dissolving. We are dissolving the sugar in the water, using the water to dissolve the sugar. Now, we're talking about here is what's happening at the molecular level. The water molecules are interrupting the interaction between sugar molecules. There's no chemical change going on here. Before you have sugar and water, after you have sugar and water. What's different is that what you now have is a mixture. And if you stir it up well enough, you'll have a homogeneous mixture. With a microscope, you can't distinguish one part of the solution from another. Yeah, and we call that a solution. In this case, it's a liquid solution. So way back to the term saturated solution, it turns out water has a limit in terms of how many sugar molecules it can separate from each other. You keep adding your sugar, eventually you'll get to the point you don't have enough water molecules to do it. And when that happens, the sugar just stares at you and laughs and says, you think I'm going to separate from my neighbor? You're only 3 water molecules. I need 100 molecules in order for you to separate me from my neighbor. So it doesn't happen. And you have a saturated solution where if you were to add more sugar, it wouldn't dissolve. You've reached the limit of solubility. Oops, there's another term. Solubility, define that.
How easily it can dissolve?
Damn, excellent. Love it. Yeah, the ability of a solute to dissolve. Is it soluble? That means it'll dissolve well. Is it not soluble? That means it won't dissolve well.
Okay.
And again, we're talking about interactions between molecules, aren't we?
Mm-hmm.
And the general trend is
stickiness.
And the stronger the interaction between the solute and solvent,
then it'll dissolve.
Next section, concentration.
What about terms. An unsaturated solution?
Unsaturated solution, that's what it's like before you hit the saturation point.
You can keep adding sugar and it will keep dissolving.
Correct.
Okay.
Excellent. All right, more terms. Here we have the term concentration.
Is that when you're thinking really, really hard?
Equation right here. It says amount of solute divided by the amount of solution.
So that gives you the concentration.
Yeah, say you had 100 grams of sugar in 200 grams of water. You could calculate your concentration. It would be 100 divided by 200 grams per gram.
1/2.
What's important is that
1 to 2?
What the idea is, the amount of solute divided by the amount of solution, right? It's a fraction. Now,
twice as much.
Stop that. So notice the units here. It's real important. What we just talked about, that Tracy's trying to figure out, is 100 grams of sugar divided by 200 grams of water, right? That's a unit of mass divided by a unit of mass. Fine, go ahead and do that. That's good. But the convention is to talk about the amount of solute in terms of its mass, and to talk about the amount of solution in terms of its volume. And note carefully, we're talking solution, not solvent. So typically, concentration is given as the amount of solute divided by the amount of solution, not solvent, solution. Now, why does that make a difference? Consider you've got 100 milliliters of water, right?
Mm-hmm.
Okay. Now you're going to add some sugar to it.
Oh.
Do you still have 100 milliliters? No. Okay. As you add the sugar to the water, you're going to increase the total volume. You may have 100 milliliters of water, but after you add the sugar, the volume of solution, which is a combination of the water and the sugar, it's going to be greater than 100 milliliters. So we got to be real careful here. By convention, when we talk about concentration, we're talking about the amount of solute divided by the volume of solution, which is the combination of the solute and the solvent.
Yeah.
If you're kind of drifting off with all these terms we've been presenting to you, that's fine. It's nothing like some good alpha waves. But I'm sorry, I'm going to have to wake you up right now. The mole. The mole, the mole, the mole. The mole. Okay, do I have your attention, Tracy?
Yep, you got my attention.
Okay, we're about to define the mole. Different chemistry curricula will introduce it at different places. I like introducing it here when we're talking about concentration. The mole. Is the number, and a common unit of concentration is the mole per liter. Liter you'll get, that's a volume, right? But mole, what is a mole? A mole is a count of molecules.
A count of molecules.
Yeah, we're not talking about the mass of the molecules. Here we're talking about the number of them you have.
Oh, because before you said that you'll have a lot more water molecules than sugar molecules because they're different sizes.
Chemists are typically interested in the number of molecules that are there.
When they're interacting with another number of molecules.
Mm-hmm. Well, and also when we do chemical reactions, we'll talk about this later, how it is you need to take so many of these molecules plus so many of those molecules to come up with so many of these new molecules. We're focused here on the number of molecules that we've got. Why is that? Because different molecules have different masses. And it's quite useful to talk about them in terms of the number, because if you have 5 of this and 5 of that, it's easy to keep track of. But whatever, here we go. The mole is a number, and it's our honor to introduce you to this term if you haven't heard it already. Okay, let's begin. You ready?
Ready.
What's a dozen?
12.
So a dozen is another term we use to describe 12, right?
Mm-hmm.
What's a pair?
It's two of something.
Yeah, a pair of shoes. That means you have two shoes. Okay. What's a ream?
A big thing of paper.
Yeah, 500.
Oh, 500.
Yeah, 500. When you have 500 sheets of paper, that's called one ream.
Okay.
Right? R-E-A-M. A mole, likewise, is a number, like a dozen, a pair, a ream, right? But a mole is much bigger than 12 and actually much bigger than 500. A mole is equal to 6.02 times 10 to the 23rd.
6.02 times 10 to the 23rd.
23rd. That's
23rd.
That's 23 zeros. It's like a trillion. It's huge.
That's a lot.
Why is it so huge?
Yeah, why would you want to know so many? Why wouldn't you just do 12?
Guess how big molecules are.
They're really not that big.
They're really
Okay, John, come on. We get it.
small. They're really small.
Really small.
Really small. Yeah. If you have a tablespoon of water, guess how many water molecules you have in there? A lot or a little?
Well, a lot.
More than 500.
Yes.
In a tablespoon of water, you've got about 6.02 times 10 to the 23rd of them.
You have 1 mole in about a tablespoon?
Mm-hmm.
Really?
Just one, technically 18 milliliters. In 18 milliliters of water, you've got 6.02 times 10 to the 23rd water molecules.
Wait, how much?
6.02 times 10 to the 23rd.
In what amount volume?
In 18 milliliters.
18 milliliters.
Yeah, about a couple tablespoons. Yeah.
Wow.
Now, 6.02 times 10 to the 23rd is a really difficult number to wrap one's mind around. And we had a snowstorm here and where we live, and we got 21 inches of snow?
Yes.
Yeah, it was insane. Yes. Absolutely insane. It got us wondering, how many snowflakes were in that snowstorm?
That's what we did when we were snowed in. We started calculating.
Back of the envelope
calculations. Could there possibly be 1 mole of snowflakes
in that snowstorm?
And John had a very interesting discovery, a fascinating discovery.
I thought it was utterly amazing. We went out and we grabbed a teaspoon of snowflakes and we put them under our magnifying glass and we took a rough estimate, a count to the number of snowflakes that were in that teaspoon. Right?
Mm-hmm.
Yeah.
Mm-hmm.
And from that, we estimated the number of snowflakes in a cubic inch.
Mm-hmm.
And from that, we estimated the number of snowflakes in our yard, which isn't that big.
Mm-hmm.
And from that, we estimated the number of snowflakes that were through our whole town.
Mm-hmm.
And from that, the whole state. It was a big snowstorm.
Mm-hmm. It's a big state.
Several states, in fact.
Mm-hmm.
And we found that it was a tiny, tiny, tiny fraction of a mole.
It was not even 1 mole.
It wasn't 1 mole.
21 inches covering hundreds of
square miles. Yeah.
Square miles.
Is not 1 mole of snowflakes. You would need to cover the entire planet, and you still wouldn't have 1 mole of snowflakes. You would need 6 Earths of snow. I think we calculated 1 foot deep to have 1 mole of snowflakes. Imagine 6 Earths covered with 1 foot of snow. Count all those snowflakes. You've got yourself 1 mole of them. It is an astronomically large number.
It's a very big number.
And the reason we use an astronomically large number is because water molecules, not snowflakes, are astronomically small. That within 18 milliliters of liquid water, you've got 6.02 times 10 to the 23rd water molecules.
So it's really an inconceivably large number.
Yeah, it's just way out there. Yeah.
Wow.
But if you had 342 grams of sugar,
yeah,
guess what?
Is that 1 mole?
Mm-hmm.
342 grams of sugar.
Sugar equals 6.02 times 10 to the 23rd sugar molecules. Sugar molecules are small too.
Mm-hmm.
Notice you need 342 grams of sugar to have 1 mole, but water's, because it's much smaller, you only need 18 grams to have 1 mole.
18 milliliters. Oh, 18 grams.
Which is equal to 18 milliliters.
Because of its
density is 1.
Density,
Yeah.
yep.
Do that in our head. Great. So when we talk about concentration, we want to talk about the number of molecules that have dissolved. And we use the unit of the mole for convenience. So if you take 342 grams of sugar,
1 mole,
dissolve it so that you make a solution that's 1 liter in volume, the concentration will be
1 mole per liter.
Yeah, excellent. 1 mole per liter. Okay, that's an introduction. That's a decent introduction.
Very good.
You kind of went on about the mole itself, but you'll find calculations you can practice those concepts with in the textbook, at the homework practice sessions at Conceptual Academy, and also from your instructor.
Awesome.
All right, moving right along, solubility and temperature. This is an interesting concept here. It's that when you increase the temperature, you might expect that the solubility also increases. And that's commonly the case, as with sugar and water. You can think of it this way. As you increase the temperature, you're making those water molecules more active, more kinetically charged. They're just moving faster. Moving faster, yeah. And they can pow, pow, pow against that crystal structure much more effectively. That's the case when you try to dissolve sugar in water. You know sugar dissolves better in warm water than it does in cold water, right? Mm-hmm. But here's where it gets interesting. You try to dissolve salt, sodium chloride, in water, the temperature makes little difference. Isn't that interesting?
Yeah.
Because the attractions that the ions have from themselves is just so relative to the attraction between water molecules themselves. It gets complicated, actually.
Wait, so does sugar have ionic bonds?
Sugar is a covalent compound. It's a covalent molecule.
Okay.
And it's very polar, I dare say. Notice what phase sugar is in at room temperature.
Solid.
Solid, yeah. Notice what phase water is in at room temperature.
Liquid.
Yeah. So sugar is a solid at room temperature. It's polar. That tells us the attractions between separate sugar molecules is huge. They stick together like crazy. Now, you're not learning anything new here when we say that sugar is sticky. Mm-hmm. Right?
Right.
You add a little water and you have water sticky, sugar sticky. It's
all over
sticky.
you.
Yeah.
Okay.
So sugar molecules, they are attracted to sugar molecules, and that makes it a solid at room temperature.
All right. There's a cool picture here where you're showing a dish that has acetone nail polish remover in it, and then you have a styrofoam cup in there.
I'm melting.
It's melting.
No, it's not.
All right.
Sorry.
So either way, I have a weird question. Is that one way to get rid of styrofoam? Because it's something that doesn't decompose.
Well, what you're doing is you're dissolving the styrofoam in the acetone. You still have the styrofoam. Once the acetone evaporates, you're going to have the remaining styrofoam still there. Yeah, though no longer puffed up. It would be a way of moving the styrofoam, but that would mean at the recycling plant you would need a heck of a lot of acetone, which is expensive, and the fumes are not fun to breathe.
Yuck. Okay. All right, but you started to say that it's not melting.
Oh, it's not melting. You take a styrofoam cup, put it in a dish of acetone.
Nail polish remover.
Yeah, and you'll find it starts to
dissolve.
It almost looks like it's melting, but it is not melting. It's dissolving. Technically, the solubility of styrofoam and acetone is not that great. And what you're actually looking at there is what they call slippage. Don't worry about it. It's just that the macroscopic form is being lost.
It looks cool, though.
Yeah. Oh, here's one other thing we should talk about. We're almost there. Solubility of gases. Now, remember how oxygen is nonpolar?
Mm-hmm.
How can you get oxygen to dissolve in water?
Well, you mix it up. Okay, so wait, induced dipoles.
Dipole-induced dipoles. Excellent. It's the dipole-induced dipoles that hold oxygen within water. Now, those dipole-induced dipoles are relatively weak, so the amount of oxygen you can dissolve in the water isn't much.
It's enough for a fish.
It's enough for a fish. It's not enough for a human. You breathe the water, there's not enough oxygen in that water to pass through your lungs, and that's not good. But for a fish, it has a gill with a different biology, a lot more surface area. It's able to pluck those few oxygen molecules out that are dissolved. Is it possible for a fish to drown?
Of course.
How so?
it doesn't get enough oxygen.
Should I tell you the goldfish story?
Okay.
It's all made up. This didn't really happen. How to kill your goldfish.
Ew.
Just take some water and boil it. And as it boils, any oxygen that's within that water is released. You are deoxygenating the water. Now, wait a second. Doesn't water have oxygen in it all over the place? Isn't water 88.8% oxygen?
But it's bound to the hydrogen.
I'm getting confused. If water's 88.8% oxygen, how come we can't breathe water?
Because it's bound. It's in a covalent bond. It's not oxygen anymore.
Oxygen? You mean O2? You mean diatomic oxygen molecules? So we got to be really careful with our language here. When we say we breathe oxygen, we're not talking about the oxygen in a water molecule. You breathe oxygen, you're breathing O2 molecules, which is a gas at room temperature. It's not H2O, it's O2. Now, the fish need O2 also. The oxygen binds to the hemoglobin and it runs all sorts of things in our bodily functions. We need it for energy, right? We need oxygen or we die. Now, cut open a fish, if you ever do that, you'll see the blood is red. Why is it red? Because of the oxygen that it has absorbed from the water. That oxygen, though, that it's absorbing from the water isn't the water molecules. It doesn't break down water molecules. Water molecules stay intact because the covalent bonds between the hydrogen, oxygen, and hydrogen atoms are really strong. Just as you can dissolve salt in water, you can also dissolve O2 in water. And that's why you see in an aquarium, you'll see an aerator, bubbles, 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 bubbles. Name that movie?
Finding Nemo.
Aerating the water. It's adding oxygen molecules to the water, and you have a mixture of H2O plus O2. And it's the O2 that's dissolved in the water that the fish take in through their gills. Notice I didn't say breathe. So you're boiling the water, the pot of water, and as you do that, all the oxygen that's dissolved in there, the O2 that's dissolved in there, will come out of solution. Now, put plastic wrap on top of the surface of the water and now let it cool down. The plastic wrap is there so oxygen from the air doesn't get back in. And as that water cools back down, there's going to be no oxygen in there, very little oxygen in there, not much. You have de-aerated the water. You have, let's say, deoxygenated the water. We have this activity we do in class where I'll ask students to pull out some paper and a pencil and draw a cartoon of deoxygenated water. A cartoon of deoxygenated water. Now, typically a student will draw an oxygen atom leaving the H2O. But guess what? After that oxygen atom leaves the H2O, it's no longer H2O. It's no longer water. If you deoxygenate your water by removing the oxygen, you no longer have water. You've destroyed the water. In this case, when we talk about deoxygenated water, we're talking about removing any O2 molecules that might happen to be dissolved in the water.
Oh.
So that after you remove those O2 molecules, the water's been purified. Just plain old water without the oxygen O2, meaning we need to be careful with our use of language. Now take your goldfish.
No. No.
Remove the plastic and hold the goldfish over it and say, "Hey, Goldie, would you like to go for a swim?"
No.
What's the goldfish going to say?
No.
Because that goldfish has had chemistry. So you carefully...
It saw you boiling the water.
So you nicely take that goldfish and you put it back in the aquarium where it is aerated, because you know darn well that the goldfish would drown in that room temperature water that had been boiled because there's no oxygen O2 in there for it to take in through its gills. Yeah, fish can drown.
Which we see that happen in the environment when you have algae blooms and stuff like that.
This was called a biological oxygen demand, the BOD. If you have waste products within the water, you'll find that the oxygen is consumed by the algae and other microorganisms through the decomposition process. And because the oxygen, O2, is being consumed, it's no longer available for the aquatic life. The fish will drown, right? So real important we keep our water systems clear of pollutants for that reason, including fertilizers for that very reason, because we know fish can drown, and we now have some insight as to how so. Gases can dissolve in water, absolutely. But how they dissolve in water is really a function of temperature, too. The higher the temperature, the less it's able to dissolve, which explains one other interesting item: oceans in the tropics. Because the water is warm, you have a decreased solubility of O2. That means you have less oxygen in the water in tropical areas than you do in polar areas. In polar areas, the water tends to be oxygen-rich. Why? Because the water is colder. And there are other reasons, too, like upwelling and currents play an important role. Anything biological is going to be complicated, I guarantee you. But it is true that with warmer waters, you tend to have less oxygen. And because you have less oxygen, you tend to have less stuff growing in that water, which is how it is. Tropical waters tend to be much more turquoise blue.
They're called deserts.
Yeah, deserts. We were in Hawaii, and we thought, wow, all this water here, there's surely a lot of fish. And really, relatively speaking, there aren't. Because it's warm, that's not good, because the oxygen goes away and you're affecting the food chain.
There's still a lot of fish.
Enough fish to make it
but nothing like what you
your
would
vacation
see
worth it.
In the temperate areas.
All right, and then there's discussions here about how soap works. There's discussions about how we purify water.
Hard and soft water.
And then there's discussions of how to make fresh water out of salt water, a reverse osmosis. Maybe we should just wrap up with reverse osmosis a little bit. Reverse osmosis is a little bit more complicated. Maybe deserves a word or two. Then we wrap it up. How you doing?
I'm doing good.
Okay, imagine a glass of water. And in that glass of water, we're going to partition it into two sides. How are we going to partition it? We could put a metal plate down the middle, down through the middle of it. So you have a left side and a right side. Right?
Okay.
But rather than a plate, we're going to use a plate that has these tiny, 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 tiny little holes in it. Mm-hmm. So tiny that water molecules are going to actually be able to pass through it from one side of the glass to the other.
All right.
Now, they're really tiny, so that those tiny water molecules can pass through. But
what's really tiny? The holes in the plate?
Yeah, the holes in the plate. Yeah.
Okay.
Yeah. But on one side, we're going to start adding salt water.
Mm-hmm.
Okay, so we just added a bunch of salt to one side of the partition.
Mm-hmm.
Now, it turns out the salt ions, sodium ions and chloride ions, they're bigger than the water molecules. And those ions are not able to pass through those tiny little holes. So while water can easily go back and forth between both sides, the ions can't. They're stuck simply because they're too big. Yeah.
Even when they separate?
Well, we know we have a solution of sodium and chloride ions, right? And those sodium and chloride ions are just floating around. And note, they're floating around with a sphere of water molecules around each of them, which makes them even bigger. So it just is very difficult for those sodium and chloride ions to pass through those tiny little holes because they're just too small. But the water molecules can go back and forth. Got that scenario?
Okay.
So what's going to happen next? Understand that water will always go from where it's concentrated to where it's less concentrated. I'm not talking about the concentration of the salt. I'm talking about the concentration of the water. On the left side, you have pure water. On the right side, you have salt water. Where do you have more water per volume?
On the left side.
Yeah.
On the side that has just
pure water. So what's going to happen is water is going to migrate from where it's pure into where it's not pure. Why? Because it's following a concentration gradient. It's going from where it's more concentrated to where it's less concentrated. Water is less concentrated in the salt solution.
Mm-hmm.
So what happens is the salt side begins to collect water molecules.
Mm-hmm.
And you'll find that the level of solution begins to rise.
Mm.
What's happening is water molecules are literally flowing from one side to the other. And because of that partition, you'll see one side ends up being higher.
Really?
You know, if you add more water to one side, it's going to get higher,
Mm-hmm.
right? But you don't have to pour water in for that to happen. It's happening through those tiny little holes. That plate, a semi-permeable membrane, permeable to water molecules, but it's not permeable to the solute, in this case, the sodium chloride.
Mm-hmm.
This whole process we just described is called osmosis.
Okay, so osmosis is when the water goes from high concentration to lower concentration. And it can pass through that plate, but it's not reversing because
No, we're just talking about osmosis here, not
just
reverse osmosis.
I'm just saying that the salt isn't going from its side to the other side because
Correct. It's stuck.
The ions are too big to get through that semi-permeable membrane.
Correct.
Okay.
Excellent. But of course, it would be rather difficult to create a semi-permeable membrane with metal. So semi-permeable membranes are made with polymers, right? But nature is full of semi-permeable membranes. Take the skin of a cucumber, eh? Take that cucumber and put it in a very, very, very salty solution. Yeah?
Oh.
And the concentration of water inside that cucumber will be greater than the concentration of water outside that cucumber.
Mm-hmm.
So water will travel down that concentration gradient from the inside of the cucumber to the outside of the cucumber. You are essentially dehydrating that cucumber, which, with a few spices, turns into what we know to be
pickle.
A pickle. Pickles are made by the process of osmosis. The skin of a cucumber is a semi-permeable membrane. All right, back to our partitioned glass of water.
Mm-hmm.
Remember, water from the freshwater side is seeping into the saltwater side. And as a consequence, the height of the liquid on the saltwater side, it increases.
Okay.
So what if we did this? We pushed down on the surface of the saltwater solution really hard. We applied pressure.
Could you squeeze the water molecules back to the other side?
To squeeze the water molecules back to the other side.
Ew.
That's the opposite of osmosis, and so we call that
reverse osmosis.
Mm-hmm. And notice what you're doing.
You're making the water go to a higher concentration.
You're making more fresh water.
Mm.
Now, let's just consider, keep pushing, and you're going to have less and less water on the one side. And you're going to have more fresh water on the other side. Why can't we just do this with ocean water?
It's like you're squeezing the water molecules out.
Yes, squeeze the water molecules through a semi-permeable membrane to make fresh water out of ocean water. And we do that on industrial scales even. It's called reverse osmosis. Now, you can do it with salt water, and that's actually rather difficult. You can do it with sort of salt water or just maybe slightly impure water, and it turns out the pressure you have to apply is not as great. It's one way industries will purify water. Rather than boiling it and distilling it, they'll just pass it through these semi-permeable membranes through a process we called reverse osmosis. That's it.
Wow. Where is that done? Where in the world
just
is that
about
done?
Any water bottling system, actually. And you can get reverse osmosis devices that you can put under your sink and do it right at home as well. You can be out in the ocean and you might have a reverse osmosis pump that if you need to survive out there and you're shipwrecked, you can transform the salt water into fresh water.
But why would you have it under your sink? Is that to purify the water?
Mm-hmm, to purify the water. You can use a Brita filter using charcoal to remove stuff from your water. Or you can have a reverse osmosis device underneath that does pretty much the same thing.
Ew.
And get this, a lot of bottled water is simply water from mountains that has been passed through reversed osmosis and marked up 3,000% in price. Pretty silly.
And then driven all around.
Oh, moved from one part of the planet to the other.
In plastic
carbon
bottles.
dioxide in plastic bottles, not good. Please consider getting yourself one of those reverse osmosis devices to put under your sink.
You get your own bottle.
Glass water bottle that you
fill it up.
carry with you. Yeah, fill it up with your RO water. Yeah, so that wraps it up for this chapter. We covered first the dipole-dipole, ion-dipole, dipole-induced dipole, induced dipole, induced dipole. Then we went over a bunch of terms that included solution, solubility, concentration. We learned about the mole. We learned about how solubility and temperature are related. And next time, we're in this podcast series, we are going to be looking at water itself. Many of the remarkable properties of water.
Wouldn't be here if we didn't have water.
Thank you so much for joining us here at the Big Picture Podcast. Till next time, good chemistry.
Good chemistry.
Our theme music by Zach Jeffrey. Musical flourishes by John Andrew from his Green Grass of Home album. Production assistance from Greg Simmons and C-Pro Music. As always, show notes are available at conceptualscience.com. And that includes samples of student cartoon drawings of deoxygenated water. A note of appreciation to all instructors using Conceptual Academy. Thank you for your support. And to the hardworking student, our thanks to you as well for your learning efforts, which we see as the path to making this world a better place. There's a bigger picture. That's good chemistry. Good chemistry to you.